Yeah. Uh, that other join. Will wait. Yeah, is it?
Can I start?
Yeah, yeah. Good morning. Now, come to our friends. Myself, I had been running all neuron electronics industry. Any is important to know industry. Today, we have met Mr. Kumar, who is having 15 years of experience in the area of construction. A brief to our speaker is in electronics, then his master's ME or drive PhD result going into the career as designer at then he any like I about the yeah
The voice is not clear.
just a minute.
voice is not clear.
Yeah, now it is clear, right?
Yes, sir, it is clear.
Yeah, probably you might want to.
Yeah, I logged in using a second device. That's why. Okay. So my friend, Mr. Vinay Kumar, his expertise in power electronics and drives. So he started his career as a design engineer at Web Peripherals Limited, Bay Mysore. Then he moved to iRobotics Private Limited. He worked in GE Healthcare, American Power Conversion, Bangalore, HBI Power Systems. Then he moved to US and he worked at Abbott Laboratories. Now he is working as senior electrical engineer at Varian Medical Systems, Los Angeles. Over to you, Mr. Vinay.
Yeah, thank you for the introduction, Gokul. I have about 15 years of experience in industry, and I have been there from 2004 with a little breaks in between. But my main expertise was in power electronics and drives. So I have mostly, in my experience, I have done mostly power electronics related stuff only. So most of my work in the industry has been on power electronics. So the background behind this presentation is that I give you a brief introduction of what are the different industries that you can look into for power electronics. In case you want to pursue your career in power electronics, what are the different industries where you can get your opportunities? Can everybody mute, please? Thank you. If you have any questions, please you can either send them in chat, or you can probably let me know at the end of the presentation. Let me move on. So what are the different applications of power electronics in the industry? Like you can see the power electronics everywhere. Like if you see around, even in your phones, you have power electronics actually is what? It is just a conversion of the power from one to another, right? So that's how the power electronics is being defined. There's actually earlier it was like thought of something which is only at a higher power level, but now the lines are being blurred, and you will see that power electronics in terms of the switch mode power supplies or inverters, you will see different applications of the power electronics in your day-to-day life. You see a cell phone charger, it has an SMPS, which is a power electronics device. Then you see any your cell phone. Your cell phone is it has at least 4 to 5 different power supplies which are there. Like within the board, you have to supply to your processor, you have to supply to your memory. All those things will come into the field of switch mode power supplies. Now I have just given a few applications. Like if you take in terms of transportation, you have automobiles, airplanes, and railways. Everything where you have power conversion. You see the electric vehicles, they work on the drives which are maintained by the power electronics. So where you convert the DC from the battery, and then you drive the motor. The motor could be an induction motor like in the Tesla vehicle, or it could be a simple brushless DC motor like in Toyota Prius. So it could be anything. These are like some daily things which you can see. You go into a railway coach, you sit in a AC compartment, or you sit in any compartment. You see the fans, how are they running? They are running just because of the conversion which is happening from battery and onto your AC supplies, right? So there is an inverter already which is there in railways. Again, in any rail coach, you have HVDC transmissions which happen, which is like your utility from one place to another place. If it is very huge voltage, now there is a HVDC transmission which happens from one place to another place. You have inverters which are going on. You might already have inverters at home, right? And renewable energy conversion is something that is picking up late because of the solar energy kind of revolution that is happening in India, especially. You see that there are a lot of solar plants being installed, and then all the solar plants need some kind of an inverter which has to convert the DC energy into the AC, which is used by your household, right? So those are like different applications where you can observe power electronics. I would like to present the product development perspective of how you develop a product, like be it this could be in general, like when you see whether it is a power electronics device, or even if it is a simple analog device, or even digital device, any kind of a device. This is the whatever you are seeing right now is the kind of a product development procedures that are followed wide in the industry. So it starts with specification. What is a specification? It is to define what exactly are you going to do. So let's take like a simple cell phone charger. So you want something that gives 5 volts, right? 5 volts, and maybe like the older chargers, they had like 1 amp, 5 volts 1 amp, or 5 volts 2 amps charger. So you have an input which is like 230 volts, and then you convert it to a 5 volts DC and a 2 amps. So which is like, so what are the different things which will come in the specification? I'll later describe that. Then you go to the proof of concept. This is a case where you propose something new in the industry. Let's say you have come up with something like a new type of topology in the conversion. So you want to do actually how it works. You want to know. So before you release to the market, you want to first test it for yourself and then see whether it works, right? So that's where the proof of concept thing comes. Then once you have proved it, you go into the circuit design part, where you actually design the circuit for the given specifications which are there. And that could also it could also imply that you should be doing some kind of a simulations where you have to do be it a ORCAD P-SPICE simulation, or some kind of SPICE simulation, where you will see the given inputs give the proper outputs, right? And later do that, you do the PCB layout and fabrication of the PCBs. PCB is printed circuit boards. I hope everybody is aware of that. So printed circuit boards, then you do the layout, then they get fabricated and assembled. And after that, you do the design verification, which is against the specifications that you have written. And imagine a system integration is like, let's say, design verification is like just testing. Okay, if I have a 5 volts, am I able to load it to 2 amps or not? That is on actually the SMPS level kind of a verification that you might do. When it comes to system integration, it comes like, okay, you have built a charger. Now, is it able to charge the cell phone or not? That's the user need, right? So system integration is something that you verify against the user's needs. And then once you have tested everything, then you go to a release of the market. Okay, excuse me. So I have detailed some things which are there, like in the specifications, where you actually get the customer needs, and then you turn them into electrical terminology, which is like, let's say in the same charger example, if I take customer says that the modern day chargers, if you see, okay, I put I charge it for like 5 minutes, and then it charges up to 80% battery. So that is some kind of a customer need. Then you actually convert that into your electrical terminology. Okay, for charging the battery at that level, what is the amount of power that is needed from the charger? And then those are the things that you might want to elaborate. Like, this is the amount of wattage that is needed, and then this will be the input supply. So in US it is like 110 volts, and then in India it is 230 volts. So if you want to make your product valid all over the world, then you want to do all the way from 90 volts to maybe 270 volts. So it depends on the kind of market that you want to release your product. So those kind of things will come into picture. Then you have your input to output relation. So I have especially when it comes to like these chargers or the SMPS inverters. So there will be something like the load regulation. So let's say right now your inverter is running at 0% load, and then suddenly you turn on your refrigerator on the inverter, and then that is like a immediate consumption of your current, right? So your inverter should still be able to maintain that amount of power in it, which it means that your control system inside the inverter should also be capable enough to deliver the amount of power for the required within the required time. So one good thing about the power electronics is like it combines especially like almost all types of fields that you have studied. If you see, it combines the digital, the modern power supplies or the inverters. They do have digital chips in them. Like let's say there is some kind of a DSP which is there, and then those DSPs will fire the inverter, and that will help faster in case you have to tune something or you have to do something faster. The digital implementation is very fast. Then there is also analog implementation, where you actually have to design some kind of circuit involving maybe an op amp. Can you
introductions, Charles Demogal Mr. Father, which was then witness. Video introduction. Small video సరిగ్గా లేదు. ఇంకా మనం నమ్మలే కదా.
Is my video bad?
Yes.
Is it okay now?
Yes. You can speak. You
okay.
can continue.
Yes.
All right. Okay. So so what I meant was that the specification of the I was in the topic where I was saying that power electronics combines almost everything. like analog circuits. It has a digital circuits. It also has the control systems. You might have studied control systems, so it also has control systems within it, where you actually implement like things like body plots, and then find out exactly what how is your system's response. Like yeah, in the previous example, what I've given, imagine an inverter where you have immediate load, let's say 0% to 100% load. How is your system control system going to respond? So it all depends on the feedback that you are giving, and then what is the PI or PID control, whatever is that you are doing inside the microcontroller. That is what is going to decide your system's response. So in a nutshell, what I can say is, like, if you understand, I mean, if you get into power electronics, especially like in the inverters or the SMPS side, you will definitely touch everything that you have studied in your in your engineering, I could say. Let's get back to the specifications. When I say regulatory standards are like just like the ISO standards that we have. In India, we might have some other standards. Mostly India follows whatever is there in the European standards, EU. So India has the same. I mean, they just say that in a nutshell, they will say just follow the CE marking. You might have seen on your chargers, right? You will have UL, you will have CE markings, and also those are the regulatory bodies which actually certify that the product that we are developing is going to comply with the emission standards or with the safety standards that are defined. So there are a lot of, if I talk about regulatory standards, that itself is going to take the whole hour, but I'll just leave it that. Then when you have done the specification, you get into circuit design, right? So the way you expand the circuit design is like you go through a block diagram. Initially, you go through a block diagram, like like you represent each block. Let's say there is an inverter, then you have something which is in a power stage. Then you have something which has a controller, like the microcontroller. It is a control stage. And then you have the input and outputs. There are different things that you can just depict like a block diagram. And then individually you can expand each of those blocks. Like in the circuit design, when you get into the power circuit design, you will have to choose the components so that they meet the specifications. Like let's say I have an input of 90 to 270 volts, and then I choose a component which is like which can withstand only up to 100 volts. It won't work with, right? So based on your input, you have to keep selecting your components, and then accordingly you have to select the topology that you are going to work with. Like if you see let's say if it is a very small kind of, I mean, there are different topologies if you consider the switch mode power supplies. Like there is a buck topology, there is a boost, the buck boost, SEPIC. These are different topologies you can in the non-isolated ones. Whereas in the isolated ones, you have like flyback, you have a forward converter, you have a half bridge converter, you have a push-pull converter, you have a full bridge converter. So there are like different things that different topologies, and each topology has its own advantages and disadvantages. And it can be used, each topology can be used only for certain set of power levels. Like I cannot use a full bridge topology for 10 watt conversion. It's going to be too expensive. I can use for a 10 watt conversion, probably a flyback topology is the best choice, something like that. So it depends on the experience that comes. And there are also resources over the internet. If you just check different power conversion topologies or SMPS topology, just Google for SMPS topologies, you'll find different resources that you can study through. And simulation is something that is probably, I would say, it is most important kind of a thing, especially in considering current situations. Why? Because it allows you. This. Am I audible?
Yes. Yes.
Okay.
You are audible.
Yeah. So the simulation, it helps you to realize the issues with your system before you actually do the design and do the testing of it. So when you do a simulation, you are not going to burn anything, right? So it's everything is on your computer. So everything, whatever you want to do, you can just put everything in it and then see what's going to be the output. And not necessarily that whatever you do in the simulation is going to be as is in the physical. I mean, when you do the actual development, whatever simulation you do, it need not be replicated, because sometimes what happens is the simulation models, whatever we take, they may not be proper ones. So let's say the simulation model gives the model parameters only for 25 degrees centigrade, and I try to use it at somewhere around 60 or 70 degrees centigrade temperature. The part may not work properly. So you have to take that with a pinch of salt, especially. So when you do the simulation, but the thing is, it gives you some kind of an idea whether your circuit is at least going to work or not. There are other advantages with the simulation. You can do Monte Carlo. Monte Carlo is something like, let's say there is a resistor. You say I want a 100 ohms resistor. Now, if you go and ask in the somebody, if you want to go and purchase a 100 ohms resistor, they are going to ask what is the tolerance of the resistor, right? So what is the tolerance of the resistor? So it depends on different processes, how the resistor is made, and there are different tolerances for a resistor based on the process that it is made. So the Monte Carlo will take those tolerances. Imagine I made some circuit which uses 100 ohms resistor. Now if I take a 100 ohms resistor and there is something like a 5% or a 10% tolerance, so there is a 100 ohms resistor, there is in that there is 10% tolerance, so it is like 90 ohms to 110 ohms. So Monte Carlo, what it does is it gives you the opportunity where you can expect where you can see your output with respect to these tolerances which you have defined. Like I have given a small example of only the resistor, but there are a lot of, if you take any kind of a data sheet for any component, you will see that there is a minimum quantity that is given and there is a maximum quantity that is given. So anything can fall within those places. So you have to keep give all those values to the simulation tool, so that what it does is it randomly picks some value between those and then it calculates. So the number of samples you do, the more accurate your analysis will be. And there is some these worst case analysis. Worst case analysis is like taking like in the resistor example, taking 90 ohms and then checking what is happening, and then taking 110 ohms and then checking what is happening. So you just go with the extreme cases and then you see how it performs. Then a custom-made component development is something like, let's say I design some circuit which has an inductor. Inductor usually you can purchase off, purchase on the in the stores, but most of them try to make their own inductor so that it suits their needs. That's an easy process rather than going with a store-bought inductor. You might not get everything that you need from a store-bought one. So people tend to go with custom-made components. Then once you are done with your circuit designs, you will do the schematic entry into a tool like OrCAD Capture. You might find this when you have done the PSpice simulations, right? So OrCAD is the company that has OrCAD Capture, and DX Designer is another one, which is by, I think, Meta Graphics. The PCB layout and fabrication tool. This is something like most of the times we get it done with somebody outside. So you just have to give like a board dimension, and then you create something called a net list, which is done from the previous slide from OrCAD or the DX Designer. You'll generate something called a netlist, and then you will give that input to the CAD tool, which is used for the layout. So there are different layout guidelines. Layout guidelines will be very important especially when you're doing PCB layout. So like in terms, if you are going for RF related components and layout guidelines, and PCB layout forms a very major role. And if you have got the PCB wrong, you just have to scrap it up, and then you have to respin again. So like you have to again start from scratch. What has gone wrong? You will not even know what has gone wrong. So the PCB layout process is kind of I would say very important step, especially in case of SMPS circuits or the RF related circuits. These are different steps which are listed over here, like the layout guidelines. Then there's netlist import and PCB layout verification and netlist verification. Gerber file generation is something that is done when you have done the layout, and then you have to get that manufactured, right? So Gerber file is what the PCB manufacturer needs. So when you go to a PCB manufacturer, they ask for this Gerber file. Where is the Gerber file? So you have to give the Gerber file to them, and then they will do the PCB fabrication to you, and then give the PCB back to you. Actually, if you watch online, you might find actually interesting videos about how the PCB is being manufactured, how the PCB is assembled, what are the different stages in the PCB assembly. There are different types of components also, like through hole components, and there is also surface mount components. So different components have different types of PCB assemblies. The soldering process itself is again very big topic to talk about. So those are different other things that you would consider. These three things are like straightforward, where you will design verification, system integration, and release to market. Design verification is where you do the compliance against your specification that you have taken. And then there is also regulatory testing, like you get CE mark only if you pass the regulatory testing. You get UL mark only if you pass the UL related tests. So there are bodies in India which do the regulatory testing, which is like they are called TUV. TUV in, I think, in Bangalore or somewhere. I think they do regulatory testing. There is also some other labs, like even HCL also has some of its own labs to do the regulatory testing. System integration is against the user requirements, like I told before, and then this release to market. I will pause over here, and then I'll just show you a simple boost converter. How exactly are you able to see my screen where I am showing you the converter?
No, it is only showing the PPT questions.
Okay. Give me a moment. Okay, are you able to see now?
Yes, yes.
Okay, so this is like simple converter where which has the input voltage. It's a boost converter, so it has the input voltage from 5 volts to 20 volts, and then it gives an output of like 24 volts at 1.3 amps. So this actually this is being simulated in LT Spice. LT Spice is the tool which is freely available. In fact, everybody of you can everybody.
Just a minute. Somebody is speaking. Yeah, you can continue now.
Okay, yeah. So this is like a simple example which I have downloaded, and LT Spice is freely available. Everybody can download it. You can just go to Analog Devices website, and you can search for LT Spice, and then you should be able to download it. And they have a number of examples which are related to any kind of converter you take. You find an example for that, and it is very easy to simulate using this tool. PSpice is kind of licensed. It has a lot of you have to invest some money into it, but this is free. So go ahead, explore this tool. You will enjoy this one. You can actually also check some videos on this one, how to do. So some things which I would ask you to get familiar with is the transient analysis, which is the time domain analysis, which they call it. And there is also Monte Carlo analysis, which I explained before. And there is also worst case analysis. So these are three things which most of you, it would be helpful in the industry perspective, if I would say, if you can get familiar with, and it will have some brownie points. So let's just see, like, these. Yeah. If you see, like, have your input over here, and which is like to 12 volts, and then the output is being boosted to 24 volts, right? How to do the design is being it actually can be if you see into the application note, you get you check this IC, and if you go through the Analog Devices website, you will find the application note related to this. There is also a data sheet for that. Let me just pop up data sheet. Data sheet is something like this, right? So this is the data sheet of the linear technologies. Linear technology is being acquired by Analog Devices. So this is the data sheet of that switch which I had shown just now. So if you go down, like I said, there are different things, right? You have a minimum, maximum, and there is a typical. So all those things might be included in your model that is being there. And if you have more questions, you can definitely ask you can send an email to the customer representatives, and then they should be able to get back to you. if you have any kind of queries. The data sheet is something which details each and every function of the chip. It also has some graphs which will give you some kind of an idea of how the device is being selected, so how the device behaves in different kind of applications. Like you see here, there is a transient load, how it is going to respond. Let's say there is an input of 12 volts and output is 48 volts. They have created some kind of a circuit, and then they checked it. These are the values, whatever you are seeing, these are the values that you will see whenever that they have seen when they have done the tests. So they have developed some 12 volts to 48 volts boost converter, and then they had checked for the current transients from 160 milliamps to 640 milliamps. So that's when they had checked how it's going to behave. So you will also see the internal circuit. You won't see the total thing, but at least they will give you the information which is needed for the functionality of the device for you to select it. So, and also they will describe the operation of the device, and further to that they will also help you with applications information, where they will give you the circuits. This is where application circuits, there you can find even how to design, like in case of a boost converter, what is it? So V out is defined by V in divided by 1 minus the duty cycle. So how can you calculate? So how can you calculate the inductor value? How can you calculate the capacitors? So those are different things that you can get the information from the datasheet of this device. What kind of capacitors you should select? How can you select the diodes? So all these will be given as part of the datasheet. And they also have some recommendations for the layout, how the layout can look like. This is like a sample layout that they have given. In all practical purposes, this may not be something that you want to replicate, but they are recommending this one. So you can check, at least if it is close to this, then they can guarantee that it is going to behave properly. So this this is something that you might want to take a look into. They will also let me just I have downloaded for the same data sheet what I have picked up. I have downloaded the SPICE model, and then this is the example circuit that they have given. Now I can change any of these. Like there are if I just give a right click on this one, and then I can pick some new diode and then see what is going to happen over here. I can let's say I want to change the inductor. I don't have a 2.2 microhenry inductor. I want something like a 3.3 microhenry inductor. I can put those values and then see exactly what is going to happen in my simulation. That's the beauty of simulation, where you can change the values and then see what's going to happen, which is great. And I think I'll take a pause over here, and let me know if anybody have any questions. If I have met what you are looking for, or if you have any other questions, probably I can cover them.
Yeah, I request the participants to unmute themselves and ask the questions or queries, anything you are having. Participants can unmute themselves and ask the queries. Yeah, Mr. T. Ravi Babu, yeah, you can unmute yourself and ask the queries. Yeah, you can unmute yourself.
Yeah, I think he was able to unmute. Okay.
Or you can just type in the chat box if you are having any queries.
Yes,
Type in the chat box.
anybody has any queries, you can please type in the chat box.
T. Ravi Babu, just a minute. His voice is not this thing. Yeah, he's not having this voice option. You can type in the chat box. You can type in the chat box.
Type in, I'll try to answer. Yeah. Any questions? If you have, you can type in or directly ask me. If I don't know the answer, I'll try to get it for you and then let you know.
Yeah, Banu, in your this YouTube link, do you have any questions, Banu?
Sir, no questions till now, sir. Gokul
Okay.
sir, no questions till now.
Yeah. Mr. Ravi Babu, you can unmute. Your mic option is not visible. You can just type in the chat box. Please type in the chat box whatever the query you are having. Okay, you can continue. Vinay?
Okay. So, so when we, I will just go. Probably, what I'll do is to just explain you how like a simple boost converter works, and then we'll go with this one. I hope you're able to see this. This is from the yes, LT Spice is a free software, and you can design your own DC-DC converter. If see, mostly LT Spice is like the company-based one. They are LT Spice is being promoted by Linear Technology. So you will find mostly the controllers, whatever they are giving, are from Linear Technology. But they do accept Spice models. If you can go online and then search for any Spice model that you have, you should be able to import that Spice model into LT Spice, and you can do your own simulation for any DC-DC converter. Yes. So this is the basic DC to DC converter. Like, you have your input over here, and there is a inductor. So basically the non-isolated topologies like the buck or the boost or the buck boost, they all can be formed only by changing these three devices: the inductor, the diode, and the switch. So these three devices, you keep moving here and there, you can get one topology. So in case of boost, what happens is boost is something that converts your input voltage to a higher voltage, right? How do I achieve that higher voltage? Imagine what happens is when there is a switch. The switch can be a transistor. It could be a bipolar junction transistor, or it could be a MOSFET. So what we do, we generally choose a MOSFET because you can reach to very higher frequencies MOSFET is particularly useful in cases where you have to switch up to like 2 megahertz frequencies. Like BJT, you cannot go beyond I think probably like 10 or 20 kilohertz, not more than that. If you go more, then what happens is the losses within the device are going to increase too much, and it won't be efficient, I would say. It's not an efficient way to do the power conversion. Whereas if you take a MOSFET, it can switch easily up to from even 10 kilohertz up all the way up to 2 megahertz. So MOSFETs are the ones which are being used nowadays. So what's happening here is when I turn on the switch, the inductor gets charged. So it is like a shot to the ground, right? Inductor gets charged because there is no charge within the inductor. Then the inductor keeps charging, and then when the switch is turned off, what happens? One thing you should always remember is that the inductor current should always be kept in the same direction. So in order to keep the current in the same direction, now the inductor is not charging. What happens is, in order to keep the current in the same direction, the voltage across the inductor, it just reverses. So what happens is, till now it was being charged by some current, and then you have some voltage across the inductor, and that voltage reverses. So the apparent output voltage what you get is Vi and VL, which is your output voltage. Here if you see some waveforms, probably it might be a little bit clearer. So when I turn on the switch, this is when the inductor is charging. This is the current, inductor current, and this is the voltage across the inductor. So when I turn on the switch, the inductor is charging. The voltage across the inductor is Vi, which is your input voltage, right? And when I turn off the switch, the inductor immediately reverses, right? In order to keep the current flowing in the same direction, it reverses. So give me a moment. Yeah, so when it reverses, what happens is the inductor is discharging along with some amount of current which is from the input source. So this is the waveform of the current when you see through the inductor, and this is the waveform of the voltage when you see across the inductor. So this is how actually the power conversion happens. Now there are some equations of through which you derive finally that V0 by Vi is 1 minus 1 by D. D is your duty cycle. Duty cycle is the ratio of your on time by total time period of your waveform. So that's how the boost converter works. Now in case of this circuit, the switch which we have told is inside. Like if you see the data sheet, you will see that they have the switch which is inside the chip. So the switch turns on and off based on the control system within that. Now what's happening here is your input voltage when your switch turns on. If you see, let me just zoom this up only to give you some very little amount of let's say I'll do only up to 100 microseconds. And let me run this one. You will see the waveforms, how they vary. So when you take the 100 microseconds, within 100 microseconds, it was not. If you see across the switch, now I want to see the voltage on the switch. If you see the switch voltage, this is how it looks. So so you see the switching waveform happening right there, right? This is where the when it goes to 0, that is where your switch has turned on, and then this is where your switch has turned off. Now on the same thing, I'll superimpose the waveform across the inductor. Let me see if I can find some differential there. So this is, I already have the V in, right? So what I have to do is to add another plot. If I just add a trace over here, which is the this is your inductor voltage. So if you see the VN001 is your voltage on the switch, and VN001 minus VN, which is your voltage across the inductor. So I've just taken the voltage difference from this point to this point, because your switch is here only, right? So it is the same node. So I can take this voltage minus this voltage is the voltage across your inductor. So this is your voltage across the inductor. Like I said, your voltage across the inductor, whenever your switch is charging, it will go all the way to like your input voltage, and then when your switch is turned off, the inductor discharges, right? So that this is the positive voltage which comes on the inductor. Now if you see the current, this is the current of the inductor. You see the inductor is charging, and then the inductor discharges. So these are like different things which you can explore within the tool, and you can actually do instead of having say 1 microfarad, what is going to happen with 10 microfarad, or else let me just do this. Instead of 2.2 microfarad, sorry, microhenry, what if I put just 10 microhenry? You can check that and then see how it behaves. Give me a moment while it generates. Yeah. So you see the waveform difference between the earlier one and the current one, and then if you see even the inductor current also keeps changing, right? And the earlier one, your inductor current was different, and then the current one, the inductor current is different. So this is the circuit that I was thinking to explain, and I hope everybody has understood what I was intending to say. With that, I think I will stop, and let me know if any of you have any questions. One more resource with respect to the give me a moment. If you want to find out easy way to even learn the layout tools. KiCad is something like an open source. KiCad is a open source where you can learn your own, do your own schematic capture, and you can do your own PCB layout. You will be able to even generate Gerber files, everything from this, and all that you need is only sending the Gerber files to the manufacturer, and then you can get your own Gerber file, own PCBs made. So in case anybody is interested in getting your own Gerber files, I mean, getting your own PCBs, doing your own PCBs, this is a good tool. It's an open source one, and you should be able to easily get that.
Yeah. Hello.
Yes, yes.
Yeah, anybody having queries, please unmute yourself and ask, or you can type in the chat box. Zakir Hussain. Please unmute yourself or just type in the chat box. If you can type in chat box also, it is okay.
Okay, sir. Thank you.
Yeah.
If you are able to ask, you can ask directly. You need not wait to type in the chat box. Thank you very much. I hope I have given some kind of a direction or at least some kind of a tools that you can use. Hope you'll find them good, and then happy learning.
Yeah, Zakir Hussain, you can unmute yourself and ask the question. You're having some queries, I think.
Or at least some kind of a tools that you can use. Hope you'll find them good, and then happy learning.
Yeah, Zakir Hussain, you can unmute yourself and ask the question. You're having some queries.
Sir, Gokul sir.
Yeah.
One person posted one question in the YouTube.
Yeah, you can ask.
Sir, that is, sir, how can we use this power electronics in automation?
Automation. Power electronics, usually automation is done whenever you do repetitive tasks, right? So whenever you do in power electronics testing, we do use automation. One thing that I can say, let's say I have some power supplies, and then I have some loads which are there. What I can do is instead of doing manually turning on and off, let's say I want to automate something like I do some 1 million times of turning on and off of the load, and then see whether the system is going to be stable or not, whether it is going to stay put or not. So in that case, what I can do is I can automate the load side, and then I can do the testing of the power supply. Like imagine doing manually, turning on and off the load 1 million times. You can do that using automation, like with a small Python script, you should be able to do. By the way, if you are interested to do automation in using Python, some tools are available. Like you might want to go for NI 488. 488 is the Visa library from National Instruments. These are like generic ones. You should download these. And then there is something called PyVisa, P-I-V-I-S-A. visa. This can control your instruments, and you can write a simple Python script, and you can control your instruments using general purpose interface board, which is GPIB, or you can use RS-232. You can use your Ethernet USB cable. You can use all these kind of instrument methods to just control your loads or power supplies, anything.
Yeah, one more question, Mr. Vinay. Somebody is asking, how is Simulink, MATLAB Simulink different from PSpice?
Simulink, I would say, see, in terms of deep down inside, if you see, MATLAB Simulink is based on matrices, and then PSpice is based on nodes. So nodal analysis versus the matrix multiplications and realizing your circuit in terms of matrices. Otherwise, I would say the why you have to in Simulink, if you see, when you do the when you try to run your simulation, then it will ask you what are the different techniques that you want to use. Like there might be some Ranga-Kutra method, or some integration methods might be there. So all those will be listed within Simulink, where you will try to achieve some kind of convergence for your output. Whereas in PSpice, it just states like the nodal values of your circuits, and then it tries to compute. Even there also, sometimes you will find that your output is not converging because of some kind of an error within your circuit itself or within your model itself. But otherwise, Simulink and PSpice, they are totally different. But however, they can analyze some circuits in common. Like if I take like a half wave rectifier or a full wave rectifier circuit, Simulink also does the same thing. But if I want a Monte Carlo analysis kind of a thing, Simulink cannot do that. You have to use a PSpice simulation.
I'm Surya Prasad speaking, sir.
Can you guys?
Yes.
Hello, am I audible?
Yes.
Yes.
Yeah. I want to know that for hardware implementation, is it essential to do a PSpice simulation, or Simulink simulation will be enough?
So it depends on what kind of circuit you are designing. Let's say if it is like the analog and digital kind of a circuit, if you want to implement that, PSpice simulation is a better option. But if you want to implement the control circuit of that, let's say I want to implement the digital control implementation of the circuit that I have designed. Like let's say in terms of an drive, some kind of a AC drive. If I want to see whether the AC drive system, whatever I have designed, if I want to see what is the response of the AC drive system, the control systems related aspect of it, the Simulink works better. So did I answer your question?
Yes, sir. Partly yes. Like I'm working on a inverter, grid connected inverter, and I'm implementing a hardware for a topology as well as the control part.
Okay.
So I'm doing my simulation in the Simulink.
So
before
yes.
going for hardware, is it essential that I should do the simulation in PSpice to know the component values?
So in terms of simulation with Simulink, if you want to see whether your control loop is working fine, you should use Simulink, because you cannot simulate the control loop in PSpice. It is not possible. it becomes too complicated. It's not like it's not possible, but it becomes too complicated. And Simulink offers very easy to use interface in that. Coming to PSpice simulation, what you can do is you can do those simulation in PSpice to understand like whether there are any kind of transient behavior. Let's say what you have to do is if it is a half bridge or a full bridge inverter, what you can do is you can just give some kind of a pulse to your MOSFETs that you have put, MOSFETs or IGBTs that you have put, and then you see exactly like what is going to happen, like how much is the loss. If you want to see exactly like what is the switching loss within the FET, if you want to explore the time domain related aspect in PSpice, time domain aspect related things, then PSpice is the best one. But there you have to just simply assume that, okay, I am giving a square wave or a simple pulse waveform, and it should be able to simulate. But you cannot simulate the whole control system. The control system has to be simulated in Simulink only.
Thank you, sir. I think I got it now. Thanks a lot.
Yeah.
Good morning, sir.
Any other questions?
Yes.
Sir, I need a difference between PSpice and MATLAB, sir. And especially in MATLAB, we can do every Simulink related PSpice, or otherwise we have to do particular only separate Simulinks we have to do in the MATLAB. Could you please just
Yes, like I said just now, it is the same. I would give the same answer. Like if you're simulating something related to control system related thing, like let's say there is a AC drive that you are designing, and the drive related control is inside some kind of a controller, right? That control principle, if you want to evaluate, then MATLAB is the best one. So, and if you want to do an analog or a simple digital circuit, the digital circuit I meant is like using some kind of a AND gate or OR gate, NOR gate, those kind of stuff, and then simple implementations of some decade counters or BCD to decimal counter, those kind of things. If you want to do, PSpice is a better one. So it depends on what type of circuit you are simulating. So if MATLAB is very good for control related ones, and PSpice is good for the circuit level related, like the simple analog or a digital circuit level related ones. I hope I answered your question.
Yeah, any other questions? Any other queries? Banu, do you have any in your YouTube link? Okay. Just a minute. Yeah. Okay then. Since you are not having any queries, I would like to thank Mr. Vinay Kumar on behalf of all the participants and Chalapathi Institute of Engineering and Technology for sharing his valuable time to educate our participants. Thank you very much. Thank you all the participants. Okay.
Thank you.
Vinay, you can end the session.
Thank you. Yeah, I will. Thank you very much.
You are the host.
Yeah.
If not, I will.